Hey, and welcome to Physics in the Flesh Dynamics episode on the Atwood Machine. The two masses shown below are each initially 1.70 meters above the ground, and the massless frictionless pulley is 4.60 meters above the ground. What maximum height does the lighter object reach after the system is released? Classic physics problem, just like the block on the ramp. Okay, except here we have an Atwood machine. An Atwood machine is a system where you have a pulley, a string under tension, and a block connected to each end of the string, and there's some sort of acceleration happening in the system. Now, this is a multi-step problem. It is a bit long, but I guarantee you if you just follow the steps, break the problem up into simpler parts, and just follow along, it's actually not that bad. Okay, so the first thing I want you to consider is think in your head ahead of time what's going to happen and think through the steps. Okay, so this is the idea here. We've got two blocks here. They haven't been actually labeled, but I'm going to label them for my own purposes, 1 and 2, just to make it a bit easier for myself. Now, visualize what's going to happen. You've got two blocks, same distance away from the pulley, same distance from the ground. One is heavier. Okay, so when you release this system, logically, the heavier one's going to fall. Okay, so then you ask yourself, how far is it going to fall? Well, it's going to fall till it hits the ground. It's going to fall 1.70 meters. So this falls 1.70 meters, and assuming that the string is not elastic, it does not extend or expand, okay, block 2 is going to go up 1.70 meters. Okay, and the question's asking us, what maximum height does the lighter object reach after the system is released? We know that distance is going to be at least 1.70 meters. Okay, it's going to go up another 1.70 meters after it goes up. Now, on top of that, this might go down 1.70 meters. This might go up 1.70, but there's 4.6 meters here that it can travel up to. So although it goes up another 1.7, it still hasn't reached the top of the pulley. And that's the part that a lot of people will miss with this problem. It goes up another 1.7 and there's a little bit more. If the problem was that easy, it wouldn't be asking you it. It wouldn't be asking the question at all, because that would be just doubling this answer. So once this goes up another 1.70 meters, at that point, this block's on the ground. Okay, so this isn't moving anywhere anymore, but Newton's first law tells us that this is going to keep doing what it's doing. It's going to keep accelerating. So the second this block hits the ground, the tension in the rope is going to disappear. And so block 2 is just going to keep going up until it stops, at which point it's going to turn around and come back down. Okay, so those are the different segments of this problem, and that's how we're going to solve this. That's how we're going to approach it. But we need to do this one piece at a time. Okay, so the first piece, as with any dynamics problem, you want to draw a free body diagram for each block. Okay, and that's why I've labeled them 1 and 2 to make it a little bit easier. Okay, so for block number 1, you have a few different forces acting on it, and same with block 2. The nice thing with these types of problems is that you're only dealing in the vertical direction, so we're not dealing with any horizontal forces. Okay, another thing with these types of problems, you have one string connecting two masses. So as is with these Atwood machine problems, you have one force of tension for both blocks. Now, the force of tension is different in each situation in terms of the direction it's pointing, but the magnitude is the same. Okay, the acceleration of the system is the same because we're considering that the string does not stretch. It does not shrink. It always maintains a constant length. So tension, acceleration, always going to be the same. And because they're moving in different directions but accelerating at the same rate, I'm going to let positive be a different direction for each block. So for block 1, I've got tension going up. I'm going to call that Ft. I don't need to call it Ft1 because, as I just previously stated, the force of tension is the same on both. Okay, now I've got force of gravity. There's a weight on block 1. I'm going to call that Fg1 because, after all, the block has a different weight. Okay, for block 2, I've got a force of tension going up. Same Ft, so no subscript. Block 2 also has a weight. We're going to call that Fg2. Now, different blocks are moving in different directions. Obviously, block 1's going down because it's heavier. Okay, so for block 1, I'm going to let positive be the down direction. Block 2 is on its way up, so I'm going to let positive be the upward direction for block 2. Okay. Now, same rope, same force of tension. We talked about that. Every motion's in the vertical direction, so that's done. Okay, so free body diagrams are done. Now what I'm going to do next is I'm going to start with Newton's second law. Okay, the next step after you do the free body diagrams is to do that. So let's start with mass 2 first. So for mass number 2, we've got F net 2 equals m2a. Remember, they're both accelerating at the same rate because they're attached to a extending less, I don't know if that's a word, but it's not stretching, a string that does not stretch. So a is the same for both. So F net 2 equals m2a. Now, F net 2, based on the directions we've identified for 2, up is positive, so F net is going to be Ft minus Fg. Okay, so Ft minus Fg2 equals m2a. Okay, so now what I'm going to do is I'm going to isolate for Ft. Good habit to get into for these problems. Ft equals m2a. Now, instead of writing Fg2, I'm going to replace Fg with mg, because force of gravity is the product of mass and acceleration due to gravity. So plus m2g. All right, so there's one equation. I'm gonna leave that here. Okay, so that's for mass 2. So the next logical thing would be to do the same thing for mass 1. So for mass 1, I'm going to do F net 1 equals m1a. Again, no subscript for the a. Now, for object 1, downward is the positive direction. So we replace F net 1 with Fg1 minus Ft. Fg1 minus Ft is equal to m1a. Again, isolate for force of tension. Ft. Now, I'm going to do this in a multi-step, but the idea is this. Ft is minus, so imagine bringing Ft to the right and bringing m1a to the left. That would make Ft positive and m1a negative. Okay, so Ft is equal to m1g, that's coming from Fg1, okay, minus m1a. Okay, so there's equation 2. Now we've got two equations solved for Ft. So I'm going to set these two equations equal to each other. And I'm going to go ahead and I'm going to try to find out what the acceleration is. Okay, so I'm going to go ahead and get started on that. So let's do that here. Ft equals Ft. That's equation 1 being set equal to equation 2. Okay, so if we set these two equations equal to each other, next step, m2a plus m2g is equal to m1g minus m1a. Now, you might be wondering, why didn't she collect like terms here? Why did I not factor out the m1 here and the m2 here? I mean, in a way, you're right that would simplify the expression, but on the other hand, remember, we're trying to find acceleration. And if I factor out m1, then I'm going to get m1 bracket g minus a. And that does not get me any closer to isolating a. In fact, it makes it more difficult. So don't factor it yet at this stage. We'll factor it after and you'll see how. Okay, so we're at this part right here. So I'm going to get all the a's on one side and all the g's on the other. So I'm going to take my minus m1a, bring it to the left. So I get m2a plus m1a equals m1g, bring the m2g over, becomes minus m2g. Okay, hopefully you see where I'm going with this now. Factor out an a from the left and the g from the right. So factoring out an a from the left, you get a m2 plus m1 equals g m1 minus m2. Okay, now solving for a, let's keep going. I'm going to just change this to m1 plus m2 because it makes me happy to see them in order like that. So a is equal to, divide both sides by m2 plus m1, g m1 minus m2 over m1 plus m2. Remember, I just reorganized m2 plus m1 to m1 plus m2. Same thing. Now, I have all my variables set and done. I'm going to plug in my numbers now. Hopefully you guys remember from video 65 and 64, we only had variables to deal with, no numbers. And I said, really good practice in physics problems. Don't plug in the numbers right away. Work with your variables first, simplify as much as possible, then plug in your numbers. Okay. Now, I'm going to be plugging in my numbers. G, simply the magnitude, 9.8 meters per second squared. M1 is the heavy one, that's 3.1 kilograms. M2 is the light one, 2.1 kilograms divided by the mass sum, 3.1 kg plus 2.1 kg. So it's just a math expression you need to simplify at this point. Okay, when you do that, you should get 1.885 meters per second squared. Okay, so now if you're wondering, how did that get us closer to the problem? Well, the good news is we're almost halfway through the problem. Well, maybe a little bit more than halfway, but here's what's happening. Now, take this number and think back to what we were doing when we were solving this problem. Remember, when this system is let go, mass 1 is going to rush toward the ground until it stops. Within that time, it's going to travel down 1.70 meters. Object 2, the lighter one, it's going to go up 1.70 meters, right? But we know that it's going to keep moving because this whole thing is 4.6. So going up another 1.7, it still didn't go through the 4.60 meters. It's still got a few ways to go. We just don't know how much, and that's what we're trying to find. But get this. Okay, so this is going to be accelerating up. Right now, just when the system gets let go, the speed of block 2 is 0, right? That initial speed V0 is 0. It accelerates up, and it accelerates at this rate, 1.885 meters per second squared. And we know that it's going to travel through a distance delta y equals to 1.70 meters, at least, right? And at that point, of course, it's going to be, we can call it free fall because the only gravity is acting on it, no tension. But it's going to be undergoing this acceleration as long as there's tension in the string, for this many meters with this initial speed. So what we need to do is find the final speed once block 2 goes up 1.70 meters. Okay, that's the next step in our problem. Okay, now in order to do that, we just use a really simple kinematics equation using the fact that we have A, we have the delta y, and we know V0 is 0. We have to find V. Okay, so the kinematics formula that we are going to use is 2A delta y equals V squared minus V0 squared. Okay, now we're looking for V, and at the same time, we know that V0 is 0, so that goes away, done. So it's technically already isolated for V. So I'm just gonna rewrite this left on right, right on left. V squared equals 2 times acceleration, which is 1.885 meters per second squared, times delta y. It travels through 1.70 meters. V squared is equal to 6.409 meters squared per second squared. Square root both sides, and you're going to get V equals 2.532 meters per second. Okay, all right, so after it's traveled 1.70 meters, okay, at this point, block 1 has hit the ground. It's now traveling at 2.5 meters per second. Now, you might be wondering, okay, what's the next part in this problem? What's the next step? All right, so let's take a look. This hit the ground. This went up 1.70 meters. At that point, when this hits the ground, the tension in the rope disappears. It becomes obsolete. Okay, but this thing is now moving at 2.5 meters per second. Now, it's going to keep moving now under no tension and simply under the force of gravity. It's going to keep moving up until its speed reaches 0. So the way you need to think about this is that this V that we just found in the second part of the story, or chapter 2 as you can think of it, this becomes the new V0 star. Okay, well, I'm going to call it V0 star because it's a new speed. This is the new initial speed for our third part. Okay, so this is going to be the new V0 star, and we know that the final V is going to be 0 because it's going to stop. And it's going to do that under the accelerating influence of gravity, moving at 9.8 meters per second squared. Now, V here is positive, and we know that represents the block going up. Therefore, the acceleration must be negative. Negative 9.8 meters per second squared. Okay, so V0 star we have, V we have, A we have, and we're looking for the distance. So we're going to use that same formula that we just had, except we're going to be solving for delta y this time. So we can call that delta y star. Okay, so using that same formula, 2a delta y star equals v star squared minus v naught star squared. Okay, so v star is 0. So 0 squared, that disappears. Okay, v naught, that's the old v. That's what this is. That's that right there. Okay, so we're looking for delta y. So I'm going to divide both sides by 2a. So minus v naught star squared over 2a. And the a is in fact g, right? The acceleration due to gravity. Make sure you plug it in as negative. Okay, so negative v naught squared minus 2.532 meters per second squared. Make sure you don't square that negative because it's outside. This square only applies to the speed. Divided by 2 times negative 9.80 meters per second squared. So the nice thing is these two negatives cancel out. So when you square the top number, you get 2 times 9.8 on the bottom. Take the quotient and you're going to get that delta y star equals 0.33 meters. Wow. Okay, we are almost done here. We've got a few parts of the story done. Now let's combine everything together. So based on our initial assessment, we've got this Atwood machine. Block 1 falls. This one goes up 1.7 meters. That's part 1. Okay, so it's already 1.7 meters above the ground. It goes up another 1.7. And then in the final instance where the tension in the string disappears due to block 1 hitting the ground, it goes up an additional 0.33 meters. Okay, so we've got the initial 1.7 that it started with. It goes up another 1.7 due to until block 1 hits the ground. And then until it stops moving, as it obeys Newton's first law, it goes up another 0.33 meters. So the total distance it travels, so we can call that delta y total, it's 3.73 meters. Okay, so therefore, the total height above the ground reached by the lighter object is 3.73 meters. So guys, I know that was a very, very long problem, but there are multiple parts to this. Just think of it in terms of steps. What happens in chapter 1? What happens in chapter 2? Think of it, break it up into a story like that. Okay, so when you do that, the problem actually doesn't become that bad. Otherwise, it's the same steps as any other problem. Okay, put your knowns, put your unknowns, free body diagrams first. Those translate into Newton's second law, F net equals ma. 2 equations, 2 unknowns, solve for your unknowns. And you may have to do a bit of kinematics in the end where you have acceleration, distance, speeds, all that's fine. Okay, but in the end, there's your final answer. If you guys like the video, be sure to click that like button and subscribe to my channel so you never miss a video from me. Enjoy the rest of your day, guys, and I will catch you in the next video.